All right. Thank you for coming. Happy Tuesday of the time change week, which is nobody's favorite, but we made it. Hooray. An announcement for you. This is happening after this class. It's an event in the library. I think you might need to register. There's a good chance you got an email about this, probably. So check that for more information. It's right after this class. I would go if I could, but I can't. So I just wanted to send that to you. I'm grading things. Thank you for your patience. I'm hoping that tomorrow is the big grading extravaganza, hopefully. And just a note, because I'm looking for at least one assignment, just make sure that you like snap a picture of any handwritten thing before you turn it in, just in case. Because this problem is solved with soft copy things that you turn in where like you've always got that document, but if it's handwritten, then yeah. So just in future, make sure that you do that. The other thing that I'm supposed to remind you of is the video is due on Thursday, right? So make sure that you're starting to wrap that up, starting to record. Let me know if you have any questions. Again, we're going to try and keep it under 5 minutes where possible. So if you want to talk to me, if it's overly long, I'm happy to brainstorm things. If you have questions about implementation or like what you should say, again, come talk to me. I'm hoping to have a little bit of time at the end of class today where you can ask me those questions. Okay, so we'll talk about the general plan for a second. Today we're doing divide and conquer today and maybe Thursday, depending on how far we get. And so with that, homework 4 is assigned. Homework 4 is now on Canvas. So we've got a new module. Divide and conquer. And so we've got the PowerPoint, the packet, got an assignment for the packet and the homework. The homework is very small. It's only 2 problems. So I'm going to give you a week from today to do that. Yeah, so it's a small homework. You've got a week. Just a reminder that I said this in a Canvas announcement to some of you. But just remember that the homework assignments are meant to be individual, but collaborative. I said that on the first day where everyone turns in their own unique paper, but you can and you should collaborate with your classmates to come up with solutions. So you can brainstorm together, but then everybody goes home and writes their own paper. That's the idea. Okay, so we're gonna do divide and conquer today and maybe next class. We'll see how far we get, how fast we go. After that, we've got hashing and random algorithms. We'll look at graph traversals and weighted graph algorithms. We'll do dynamic programming. Those are the 3 main units in the pipeline for now. They will probably get interrupted by the midterm. The midterm is planned to be the Thursday before spring break, so on week 8. That's the plan right now. And the Tuesday before, I'll give you, hopefully earlier, but at least Tuesday before, I'll give you study guide, and we'll spend that day reviewing and doing practice problems. In terms of things to expect like algorithm analysis questions, the design a data structure that does this in this amount of time, and just solving hard problems. So the things that we do in class and the things you do on homework will hopefully prepare you for that. Any question on our plan in general? Okay, I will also note that the project was assigned, so make sure that you're starting to find your group. and maybe start brainstorming about topics. That's not due until I think the week before spring break or the week after spring break. I don't remember. One of the two. Okay, so we're gonna do the slides today and the packet, and we'll see how far we get. Divide and conquer. That's us. Okay, so we're gonna do the divide and conquer chapter. What we're gonna do is we're gonna briefly review binary search, although I think you all know that already. We're gonna look at another divide and conquer algorithm that you probably haven't heard of before. And so that takes care of addition and multiplication. When I wrote this slide deck, I was staring at the word addition and I'm like, that just looks like it's spelled wrong, but I think it's not. Yeah, so we're gonna look at how we do math, and then we have problems to work on. So for this unit, we've got the packet and the homework, those two problems. And so we've seen divide and conquer before. This is binary search, where if we've got a sorted array, we can start in the middle. And if we're looking for something, we either go left or right, depending on whether the thing we're looking for is greater or less. So can I zoom in? I can. So in this example, we're looking for number 7. And so we start at the middle, and the middle element is 5. 7's greater than 5, so we go to the right. And then we disregard the entire left half of the array, and we go to the middle of that, and we find 8. 7 is less than 8. So we disregard the entire right part of that subarray. And then we're looking at these two numbers, and we find it in 7. That's binary search. So in real life, divide and conquer, there's a quote from ancient Greek saying divide and rule, which you'll see in like history if you look at like Britain and India, where the idea is that if you divide the group into divisions, then it makes it easier to control the individual parts. So that's kind of where this gets its name. But we look at the technique where like we're gonna divide it into parts and then solve the individual parts. So now I've got a question for you. And this is the first problem on the packet. We want to add two numbers, 123, 123, and 456. I would like you to talk with your neighbors. How do you add those? What's the algorithm that you use to do that? Go for it. I'm going to pause recording and do attendance. Go back to recording. How do we add these like 1, 2, 3, and 4, 5, 6? I mean, this is arithmetic, right? But I'd like to know like what's the process? Yeah. Mm-hmm. Mm-hmm. So we add 3 plus 6, we get 9. We add 2 and 5, and we get 7. 1 and 4, and get 5. Mm-hmm. So how do we add two general numbers? So write an algorithm in pseudocode to, yeah, I would like to know pseudocode for how to add these two numbers. So something that seems really intuitive, but I would like us to expand on that. So this is a situation where like all the letters are not are digits, 0 through 9. I didn't give you a lot of space on the packet to write it, so use this space. You've got options. For the people on Zoom, if you go to Canvas, we're working on the packet there. Here, I'll give you another minute to finish writing. Yeah, question. No, so like 1, 2, 3 is A, B, C, where A is 1, B is 2, C is 3. Yeah, and consider also for like a number that's like A through Z, like a really long number. Your pseudocode should be able to handle that sort of situation. Yeah. Yeah, like you can add leading zeros as needed.
What's the general algorithm, or you, so quality, the logic.
Mhm. Like for if statements? Yeah.
But you just can't use like add, can't add in an add algorithm. So,
Well, I mean, like you do need to add the numbers at some point. Like for like 1, 2, 3, 4, 5, 6. Like we need to add 3 and 6, right? So maybe we consider like a base case or of like single digits are fine.
you have to like go to like lower level.
You could. I don't know that we need to. All right. I see some people still finishing up. Let me share one from the chat. which says I would start with the smallest place and add those two numbers. If there's overflow, add one to the sum of the next place and repeat, which is like how adding works, right? I'm just trying to get you to formalize, here's how we do something like that. Anybody come up with something substantially different or something other than that you want to share? Yeah.
Wonder if we kind of think
Like a what? A linked list? I don't know that we need one for this. I mean, it's definitely possible. It just might be too much for this application. Yeah, let's see. Hash map. Elaborate. How would you use a hash map to do this addition? So let's see. The basic idea is start with ones place. Maybe so maybe we assume that single digit addition is okay. It's just when it's multi-digit, then it gets complicated. Another thing that we may want to use is consider so typically n is the size of our input, right? What would n be in this example? Yeah. The length of the number. So length of the number, or another way of putting it is like the number of digits. So we start with ones place, add that, and then carry is there a possibility that we would get greater than 1? No. Because the maximum number is 9. So if we add 9 plus 9, that gives us 18. Yeah, sorry. So if we assume that like a single digit is okay, then we start with the ones place all the way on the right and add those. If it's over 9, then we carry 1 over. And then I would say we add 1 plus result. So even then, if we add 9 plus 9 and we add a 1, that would still give us only 19. And then we just repeat that for all the digits. Sounds good? What's the complexity? This line is the kicker? Order n. Yeah. That makes sense, right? Because we have to go through all of the digits. And we have to, so for this example, n is equal to 3. And so we do this adding n times. All right. Now let's talk about multiplication. So we're on the second page of the packet now. So how do you multiply 4 by 5? You can answer in the chat. Add 4 by itself 5 times. That's an option. So either we do 4 times, wait. Hold on, let me read your message again. Add 4 by itself. So 4 plus 4 plus 4 plus 4 plus 4. Yeah. I think another way to approach this is also, do you remember like times tables in elementary school? Where there's like 1 by 1 is 1, 2 by 1 is 2, 2 by 2 is 4, and so on. We could also just, so either we could take the addition route and just define everything in terms of addition, or we could assume that we have some lookup table of, here's my times table for all the numbers. We had 0 in here, 0 through 9. So there's different options. I would say that we proceed with the lookup table assumption for the future. Because that'll make the next thing we do easier. Okay, how do we multiply 1,234 by 5,678? Talk it out, draw it. Harken back to elementary school.
Yeah, you're right. Like, oh, we had the 5,000 but I don't know. Correct.
Okay, let's be third graders again. How do you multiply these? Someone tell me the steps. Go for it.
Each place in the first number, each place in the second number.
So, and that's 8 by 4 plus, or
40, 30, 80, 200, 1,000.
yeah. And I will Okay, so this is 10 to the 0, because that's ones place. Because we're working,
The, like. What the. What with the 10 to 3, 4, all that.
mhm,
Um. And then, yeah, once you have all those products, um. For all the digits in each number, then you just add them up to the final sum. That's the result.
mhm. Okay, let me write out like how I actually do it. So 8 times 4 is, oh gosh, 32. Thank you. So you carry that. Then 8 times 3 is 24 plus 3 is 27. 8 times 2 is 16 plus 2 is 18. 8 times 1 is 8 plus 1 is 9. Right? So we get this number. And in order to represent those digits, the way we represent those is, so like this is the first digit, this is the second digit, this is the third digit, this is the fourth digit. Right? So it's all of these numbers plus some power of 10. And so if we add all those together, then we get our final number, right? So we get 8 times 1 times 10 to the 4th. What's n here? And remember, if n is the number of digits, so now n is 4. Plus 8 times 3 times 10 to the 2 plus 8 times 4 times 10 to the 0. That's how we get this number. And then, I should have left more room. And then we repeat that. So for then we do it with 7, and then we do it with 6. Just like adding a 0 across as we go. So here, let me write this out without. Okay, so we got 2, 7, 8, and 9, and then we add a 0, and then we do 7 times 4, 28, thank you. 7 times 3 is 21, plus 2 is 23. 7 times 2 is 14, plus 2 is 16. 7 times 1 is 7, plus 1 is 8. And so on. So this we'll add 2 zeros for the 6 and 3 zeros for that. So if we do this for a general number, that's the next slide. Like, we do this for a general number. How many, what's the complexity? Talk about it for a second. That's the, let me actually open up the packet. So that's the, how do you multiply them and write the pseudocode, and what's the complexity? Sure. N squared. That answer is correct. Why is that?
You're only multiplying each place by each you place on one number, right, you should operate the other number,
Mhm.
and you like, depending on how long the first number is.
Yeah.
Yeah, it's not how long it is.
Yeah, so it depends on how long the number is. You can assume that like, if I have this big number times like 5, a smaller number up top, you can assume that there's like 4 leading zeros before that. So however the biggest number is, you can consider that and just add leading zeros as necessary. Yeah, so we have this like square that we eventually fill out, where we multiply each of the numbers of, if we consider this x and y, each of the digits in x multiplied with each of the digits in y. And that's a classic n squared, right? We've got nested for loops. So yeah, that's kind of where we're at. So we talked about this, and we also talked about this. So now we get into the algorithm of a guy named Karatsuba. So the legend goes that someone was, so back in like early computing, they were really concerned about making algorithms more efficient, right? Like we wrote these algorithms, but the difference between n squared and n is a big deal. And so we want to reduce that however possible. So there was a lecture where a famous person gave on, this is why I think multiplication can't do any better than O of n squared. That was the conjecture. A kid sitting in that lecture, college student named Karatsuba, he went home and came up with a new algorithm, one that he argued was O of n to the 1.6 rounded up, which it doesn't sound like it's a lot. Wait, let me write this better. It doesn't sound like it's a whole lot better than n squared, but when we're talking with like huge numbers, decreasing this 2 matters. So having a 1.6 algorithm is important. So we're going to talk about that algorithm. We won't go too into detail about why it's n to the 1.6. It gets really complicated really quickly. So we're going to look at simple examples just to have some fun and show you that this is an algorithm that exists. So what we've done is we've multiplied every pair, right? That's how we get to n squared. Instead of doing that, we're going to use what we know about the structure of the number. So remember we talked about like, we wrote it in this form of with like n to the 4th plus 10 to the 3rd and so on. We're going to leverage that. The way that, so Karatsuba realized that you can write the answer like this, where if we have two numbers, one of them is AB, the other is CD. So again, representing like the letters as digits. We found that the result is like if we do A, B, and so like if A had added 10 to the whatever, we can FOIL this out and we get this equation. So that's how we get there. So this is all well and good. But here, if for a n equals 2 digit number, we still end up having to do 1, 2, 3, 4 multiplications, right? But he figured out a way to combine AD and BC into one multiplication. that gives us 3 multiplications total, which is faster than 4. So his solution is, here's how we're gonna do this AD plus BC. And so the solution is to first compute AC and BD, and then we feed it into the this equation where we call, here's the way that we do Karatsuba. So if this is the Karatsuba algorithm, so we do it again, but we don't do AD and we don't do BC. We do A plus B and C plus D. And then we just, because we know this is, we got this from foiling, if we were to subtract AC and BD, we would get this bit again. Okay, so let's see it used for 12 times 34. I'm only going to do 2-digit numbers. I will say that, like, so we're going to do 1, 2 times 3, 4, where 1 is A, 2 is B, C is 3, and D is 4. But you could split it up like this. So let's say we're doing a 4-digit number. You could split it up like this is A, this is B, this is C, and this is D, right? And that's where the divide and conquer comes from. Where instead of dealing with single digits, you group multiple digits together, and then you can call it recursively. Okay, so let's do 12 times 34. What do I want to do with this? Let me make a new slide. Okay, so now we still have the equations. Okay, so we're doing 12 times 34. So for this equation, we start with AC and BD. So AC is 1 times 3. And then we multiply that by 10 to the n, which is 2. 2-digit numbers. Then we add the result of this here. We'll save that for now. That's get multiplied by 10 to the, that's an n over 2. 2 over 2 is 1. Plus BD, which is 2 times 4. With me so far? We can do these multiplications easy because they're single digit. Again, remember times tables. So this is 3, and this is 8. Great. So now we just need to figure out what's AD and BC. So we do A plus C, which is A plus C, 1 plus 3, times B. No, I'm wrong. 1 plus 2. And then C plus D, which is 3 plus 4. And then, so we do that multiplication. That's happening here. And then we subtract AC and BD, which we already know. So we know this is 3, and we know this is 8. Sounds good so far? Okay, so then we just need to do this multiplication, which is 3 times 7. Lucky for us, single digits, we know that's in our times tables, which gives us 21 minus 3 minus 8, which is 10. So once we do that, we've got the thing in parentheses. That number is 10. So now we can rewrite our equation as 3 times 10 to the 2, which is 300, plus 10 times 10 to the 1, which is 100, plus 2 times 4, which is 8, which gives us 300, 400, 8. Yeah. Right, so this, so the original, it's like a 2-line equation. Yes. Just to emphasize, we'll see this in the next example of just emphasize that we have to do it multiplying this way. It doesn't really matter for this example because it end up being 3 and 7. But the next example, we'll see where it's like 11 by 15. And since those are more than 1 digits, we have to do this process again. It's recursive. Any other questions about this? Okay, so this is 408, which is correct. Hooray. Now we'll do 56 by 78, which is 4,368. Okay. So first we do AC. A times 5 times 7, 35. Times 10 to the 2 plus something here times 10 to the 1 plus B times D, 6 times 8, which is 48. I knew that because I did this beforehand and I wrote it down. So we can get the outsides quickly. Now we have to look at the inside. So I forgot to mention, on the previous one, let's see how many multiplications we actually did. So we did 1 here to do 1 times 3. We did 2 here, another here to do 2 times 4. And then we ended up doing 3 in the 3 times 7. Instead of 4, which would have been 1, 2, 3, 4. So we only did 3 actual multiplications and we just saved those results. And that's why we don't count 3 in the 8 there. So doing 3 instead of 4 for a 2-digit number is an improvement. For an n-digit number, it reduces it, which is great. Okay. So now we've got to do the parentheses. So A plus B, which is 5 plus 6, that's 11, times C plus D, 7 plus 8, that's 15. Right? These are both 2-digit numbers. We can't simply do this. So we have to do Karatsuba again. But before we do that, we have to subtract AC, which is 35, and BD, which is 48. So 11 by 15. Again, we split it into A, B, C, and D. And so AC is 1 times 1 plus something times 10 to the 1 plus BD is 1 times 5. And then we do 1 plus 1, which is 2, times 1 plus 5, which is 6, minus 1 minus 5. And so that's 2 times 6, which we know because of our times tables, single digit numbers. So that's 12 minus 1 minus 5. No. Yes. 6. I think. Yeah, 12 minus 6. So this gives us 100 plus 60 plus 5, which is 165. And then we just plug this back into this part. And so now we have 3,500 plus 165 minus 35 minus 48, which per my notes is 820. Feel free to check that. Plus 48 at the end, and we get 4,368. So the heart of the carrot soup algorithm is doing this splitting into A, B, C, and D. And the divide and conquer part is we're doing this for the middle. And so divide and conquer is we're splitting this number and doing math on different parts. So now just for fun, if you want a few minutes to practice on the packet is 83 by 46 and 29 by 52. I'll keep this up so you can refer to it. I also have markers if you want to draw it on the board. It's not super critical to me that you get this like perfectly. This algorithm wouldn't show up on exam. This is more just practice, another divide and conquer algorithm. So have fun with it. It gets tricky with the- Yes.
That's what I'm lost. Not the middle part. I don't see
They
where
work
the.
together. So consider the first one. Terratuba equal, Terratuba of AB
I don't
times
see where the
AB.
10 to the 1 and 40.
Yeah, the first one is Terratuba of AB. Yeah.
Yeah, but
And then the second one is a special case.
that's inside of parentheses, and outside of parentheses. Why is that even parentheses?
Yeah, so it's like this whole second equation, you can replace AD plus BC. Yeah. Yeah,
After, like, it's already, ultimately, I can't really tell, like, one side of the step, would that just be instead of then multiply everything? That's the issue.
yeah, so the only trick is this multiplication.
Okay.
So because these are two different numbers, you have to do it again.
Oh,
Treating
So,
this one as A, B, this one is C.
oh, okay, and then,
Yeah.
and then after that, it's.
Yeah.
Oh, right, okay.
So we're only allowed to do single digits.
Okay.
Don't do the second step, even just one of the numbers, that's just. So,
Yeah.
right, so you still have to go.
You only have times tables for zero
Okay.
dot part. So you just add a leading zero. And that makes it easier.
Um,
And MIS.
And is the number of digits.
So it's done. Okay.
So it's two.
Yeah.
Oh.
Then I was wondering why we was not using that, the brand word methods.
The Tranberg method?
Stockton.
Tracton? Oh, how do you spell it again? Oh. Yeah, there's multiple ways. So once this kid solved it, then other people were like, I could solve this too. Because the conjecture of all multiplication must be n squared is false. And so, yeah.
That was faster.
Let's, see if Geeks for Geeks has an answer. Does it give me an answer? Is, I like the question, is mental arithmetic good? I'm not sure of the complexity, but that's also an option. The reason we look at Karatsuba is that's the one that's in the textbook. But there are others. Okay, did we have enough time to play around with it? What's 83 times 46? What numbers did you get?
32.
Did everybody get those same numbers? I see a no.
That's right. I just have to-
Okay, yeah. Yeah, make sure to like double check with an actual calculator. What about 29 by 52? Yeah. We get those ones too? Hooray. Great job. I put two YouTube videos that I used when I was figuring this out in the slides. So if you want to go and watch them, there's also oodles of links on the internet if this is interesting to you and maybe you want to try and beat it. Okay, so for now, we've gone through the slide deck. So now I just have some divide and conquer problems for you to work on. We've got the circular shift problem. We've got 20 questions. and we've got the sticks problem. So 3 difficult problems that we're gonna work on. So first off, let's work on the circularly shifted one. So this one assumes that we take in an array that's sorted. So 5, 15, 27, 29, 35, and 42. It's sorted in increasing order, but it's shifted by some amount k. So when k equals 2, we take, it's like we shove 42 and 35 off and put them around at the beginning again. So, and it's still in order. So we still have 35 and 42. If we shift it by 4, then those last 4 digits get pushed onto the beginning. So the first question is, if we know what k is, give a constant time algorithm to find what's the largest number. And the other thing is, if we don't know what k is, how do we find the largest number with a log algorithm? Okay, go for it. Talk about it.
Those 35. I guess you get too far, such as the ones that you don't have, what is that, you should all find a base, then should be fine, with certain dimensional.
Because I don't know how long it's gonna take to figure out how much basketball rate. So, choose a house application, if I want to do that, that would be. It's like, what is the like, girls in the rainbow? It's like pretty cheap. It's like, it's like 600. But those are mostly like an average, I'm getting that for like average, you pay on campus. Average, that and it's like your own room. You're sharing common.
Yeah, yeah. I think it's, yeah, the last case.
My memory was there. This is a sign.
Those were given. When I first used five, we go, so that's. Go through the second, we're gonna just find out, two additions of bridge. Right now, the same one. Oh, I know. And then, we look at the last one, and then apply that, so, is it that one?
No, this one needs to be. This one. So we know that that's, so I'll be. It's actually my number.
Yeah. I'm only gonna do like 500. No, they got it. It's fine. It's also not research. Yeah. Oh.
Yeah. That makes sense.
No, just the one. I'm not always back there.
All you need to do, you know, because it shifts, right? On shifts, so you're saying like, okay, well, you just check how much you shift, you know, like if it shifts 4 over, just check the fourth position. Minus, because it starts to cool, right? But then you can, you know, you get sort of like, you know, if it's shifted 9 and the list is 7, it just drops to 7, and if it's shifted, it's checking the second position. Great, because it's just checking. They don't read that, they just.
You're responsible.
Good job, right?
So,
So like, let's put it down there, so there's more than one video.
Cause that's like, yeah, you're also.
29 is very long time. And I know it's not. So.
Okay, I'm gonna give a hint to those of you who may be stuck. And there may be also be other ways, because I hear people talking over here and back there. So we need to do something with binary search, right? That's the goal. So one possibility is to look at the middle and also maybe the first and last and see where those first and last elements are in relation to the middle. Are they in order? Are they not in order? That can help you figure out where to go. That's my hint. Continue. Remember, we're using binary search. If you were talking about something else, keep going. This is if you're stuck. let's talk about it. And then I'll leave the last 10 minutes for groups. So does anybody have a solution for the first one? So if we know what K is, how can we find the largest element? This should be fairly easy. Yeah,
Take mod in.
A minus 1. Oh. And erase. Yeah. Hmm? Yeah. This is, I think this is what makes sense to me. Yeah. This is a question. I think we could maybe assume that K is less than N. Again, like, this is assuming that K could be greater than or equal to N. This is assuming that K is less than N. But it's got the same idea, right? So different assumptions affect how you approach it. All right, what about ideas for the second one? Did anybody come up with an idea with that? Anybody want to read me their solution? Even if it's incomplete? Yeah. Yeah, wait, so you said fourth index? How do we do that in general terms? Do you know? So fourth is 0, 1, 2, 3, 4, which is here. Why that index?
Is it like splits the grade.
Okay, 1, 2, 3, 4, 5, 6. I'm curious why 4 and not 3, 0. Oh wait, 0, 1, 2, 3. Like, and why not 2 or 3? Which would divide that evenly down the middle.
Because after we look at the index, I'd say we'll be looking at the left. Right?
Yeah, I would argue that you could do that regardless of what middle. So I think put air quotes around n over 2, where I think the idea is like we go somewhere in the middle. Okay, continue.
And then you want to look at the left and right index, the middle index, and check whether they're respectively less than the left side and greater than the right side. And if they don't obey this, that means you're really close to the area or the shift value.
Mm-hmm.
So what I said was, the right side wasn't greater than the middle value, then the shift is like the index minus 1, which is like the middle index.
If the right side is greater than the middle, then the shift has to be on the left of the mid.
Yeah. Then, if the left side doesn't work, then it has to be the index.
So we've got X, Y, and Z. Either, so let's say we've got an array 1, 2, 3. The options are either k equals 0. And so 1 and 3 are in order. The option 2 is 3, 1, 2, where they're out of order, which means that this is the highest value, or what's the other one? 2, 3, 1. In which case 3 is the winner. Okay. So the idea of looking at the middle and comparing the two, so this is the case for a 3-element array, but if it was like a 500-element array, any ideas for where to go from here? Or other approaches? Yeah.
Starting at
Mm-hmm.
so.
Yeah. Yeah, and so what were you doing at the quarters?
I was just comparing, I was just checking, like, once I find the quarters, I check if the elements at each quarter, the first, whether they're greater or less than each other.
Mm-hmm.
If the first quarters, less than the third quarters, then you know the numbers, the greatest numbers in between, because the quarter, you know, the numbers not in between. Because the first quarter is the same up to Q3. So there's no break in the ascension. And the opposite is true. If the first quarter is greater than the third quarter, it's ascending, then ascending and restarting, ascending is the largest elements in between.
Right, so taking different like samples and asking, are they in order? And I think this is like the standard. So we need to find, so first of all, we need to understand the base case for like, what if k is 0? In which case I might look at the first and last and see if they're in order. The other case, I think the general idea is, like we said, like look at a middle element, and look at what's on the left and right of that. And if they are, then like look at the like left and right of this and maybe the ends, and that kind of determines whether you go left or right. And then once you decide where you go left or right, then you ignore the other part and just focus on that. Yeah.
So, I mixed, so when you say going left or going right, is that when you just do like you just search the rest of the array, like one by one, or are you trying to?
Applying our algorithm recursively, because that's what binary search does.
Like go left, it's like the outside. And
Right. So like if we start here and we look at the left and we look at the right, and or maybe, ooh, this is what we do. I think we compare the left with the beginning and the right with the end. Maybe?
Right. But it's the middle is, if the beginning is less than the middle, then you know it's the right side. And the opposite, you know it's on the left side.
So we've got mid, we've got beginning, we've got end. If beginning is less than mid, go right. Is that all we need?
like, you can kind of use, like, from, if the beginning, if the middle is less than the beginning, then by that, like, you know that there's like a break, like the ascension is kind of restarting, within that, like, that's
Yeah. Yeah, okay. It's 3:10, we ran out of time. Thank you for participating. If you've got questions about your video, please talk with me. Just if you want to run something by me. Just to make sure that you don't lose points for some silly reason. I'm happy to do that. Thanks, and I'll see you on Thursday.